Good evening, all, and welcome to the first session of 2025 on this nice Saturday evening in India. Today's session is a session on Azipod electric propulsion by Mr. Andrei Korsström of ABB Marines and Ports from. He's joining us from Finland. Thank you for joining, sir.
Thank you.
And today's session will be chaired by Professor P. Krishnankutty. It's my privilege to introduce Professor Krishnankutty. Professor Krishnankutty was a professor at the Department of Ocean Engineering, Indian Institute of Technology, Madras, till June 2022, and is currently associated with the Department of Ship Technology, Cochin University of Science and Technology as Emeritus Professor. He has about 43 years of teaching and research experience in the field of naval architecture and ocean engineering. Dr. Krishnankutty completed his BTech degree in naval architecture and shipbuilding from University of Cochin in 1981. Masters in Ocean Engineering from Stevens Institute of Technology in 1988, and PhD in Marine Hydrodynamics from IIT Madras in 1993. He was a research fellow at the Department of Naval Architecture and Marine Engineering, University of Glasgow during 2001 to 2004. Dr. Krishnankutty has guided many research scholars leading to MS and PhD, and successfully carried out many research and industrial projects, and published more than 130 research articles in leading international journals and conferences. We know him well in our academic and professional circles here. And he is the Vice President of Royal Institute of Naval Architects, London, Chairman of the Hydrodynamics Panel of the Naval Research Board, Ministry of Defense in India, Member of the Research Advisory Committee, National Institute of Ocean Technology, Minister of Earth Sciences, Government of India, Member of the Lab Research Council of Naval Physical and Oceanographic Laboratory in the Ministry of Defense in India, and member of USHUS, which is a startup program of Cochin Shipyard jointly with IIM Kozhikode and IIT Madras. He also served as the Dean of Faculty of Ocean Engineering in Kerala University of Fisheries and Ocean Sciences during 2015 to 17. And he has also got various scholarships and awards, Government of India Scholarship for Studying Abroad 86 to 88, Innovation Award for Robotic Fish Development from National Innovation Foundation, New Delhi in 2014, and DRDO Award for Outstanding Contribution in 2023, which he was privileged to get honored from the Defense Minister at New Delhi. With this brief introduction of his immense contributions, now I would welcome Professor Krishnankutty to come and chair the session, sir, please.
Thank you, Dr. Bharadwaja, and thank you, the speaker, Sir Andrei Korsström. I hope I am pronouncing it properly. And I understand you are joining from Helsinki, Finland.
Yes.
Okay. Yeah. Okay. So it's a nice topic here. This Azipod electric propulsion, and so maybe we'll come to the details later after the presentation of that while summing up. So let me introduce the speaker of today's session, Mr. Andrei Korsström is the naval architect. He did his MSc in naval architecture, and he also is working with ABB OY Marine and Ports. He works as a solution and sales manager at ABB Marine and Ports, and is stationed in Helsinki, Finland. He started his career as ABB in Hydrodynamics, from which he progressed to product management and then product sales responsibility for Asia. Key aspects connecting the different positions is a deep understanding of the technical suitability of the Azipod as a propulsion solution for different market segments. So this is a brief introduction of him. I think he will, in the process of presentation, he will give more information about his work and positions in detail. So I welcome him to the session. So may I request him to take over. Please start your presentation.
Thank you, and thank you for the kind words. Yes, I'll probably fall back on comments on my previous work and so forth. And as probably most of you know, if you have ever dabbled in hydrodynamics, you don't get the hydrodynamicist out of you. It's always there. So just a second. Okay, you should see the screen now. I'll start off with a couple of words on ABB as a whole, and then start to dive deeper into pod propulsion per se. Well, settle to aim at having a roughly 45-minute session. So let's see where it takes us, and hopefully everything will be in order and so forth. So just see. Okay, so ABB is a global company today, which is basically a collaboration or merger between ASEA and Brown Boveri in the late 1980s. However, because the main concept of how the company came to is by merging existing companies and so forth, we boast a history of over 140 years. Currently, we're employing about 105,000 people. Globally, we used to be up at around 150,000, but then sold out the high power cabling to Hitachi High Power. So that's more or less in a nutshell. We have different figures on it, but basically to remember, global company. Right, so what is pod propulsion? I'll tick that down. So what pod propulsion basically is that we're looking at big, large electric outboards. I think that's the easiest way to explain the concept in itself. So on a pod, generally we have the electric motor located inside the hull, which is directly connected then to a propeller. That means that we have forward motion and also allowing for negative RPMs, so also backwards motions in that sense. Additionally, the unit is infinitely turnable in either direction. So most commonly, actually, if you want to go backwards, you turn the units 180 degrees, and hence you have the benefit of a propeller which is working in the direction it's designed for. Yes, so just to make a comparison between what's commonly also seen is azimuthing thrusters. And we see that the main principle is that on a pod solution, we basically aim to fit everything in regards to propulsion into the pod hull. So we have less equipment in that respect inside the vessel. So usually if you have a mechanical thruster or a shaftline solution for that matter, you need to be aware that you need to have a propulsion motor somewhere in your hull form, and from that you need a rejigged shaftline connection to your propeller. But this is just to highlight some principal concepts in that respect. Right, so if we start off by having a rough estimation of what a equipment solution in that respect would look like, we would have in the stern, as was shown in previous picture, a pod propulsion unit. This is the part that is seen outside the hull. And as said, it's incorporating the electric motor. That is then connected to a steering unit, which allows for that rotation to act as a steering device. Because it's infinitely turnable, we have a slip ring unit, which basically takes care of the power and data transfer down to the unit. And on top of that, we have then a cooling air unit, and on the side, some cabinets. These are basically the steering drive cabinets taking care of the steering, and then we have a cabinet to accommodate for the communication between the unit and bridge, etc. control. Of course, in this case, the power control, so how much the speed of the vessel, the power of the unit, etc., is then controlled by a larger suitable drive system, which is located slightly further up in the vessel usually. But this is a typical arrangement that you would see in the so-called Azipod room, similar to your steering gear room today in a vessel. So principal benefit is that we allow for quite a small footprint inside the vessel in that respect. Right, I'll continue with a few words on the layout. Right, so principally what we see, if we compare to a conventional shaftline solution, even in this case the shaftline solution is an electric propulsion solution, so you would have the diesel generators arranged here, and then on top of that you have the propulsion motors, which are then driving the shaft lines, propellers, and so forth. So this is a study done back in the days between by Delta Marine on what the benefits in regards of footprint inside the vessel could be for this kind of vessel. And the outcome was, when you compare it to a pod solution, you see that we actually save around 250-265 square meters of space inside the vessel. Now, this is part of the benefit of the flexibility of design. One of the other things which is, I think it's easier to discuss in this slide, is actually the fact that now in the pod solution, there is no rigid connection between the pod and the machinery space. It's connected, of course, with electric cabling, but it allows for the freedom of placing the pods, placing the engine room where it's most suitable for the design. So for instance, if you look at the resistance optimizations, the fact that you don't have this rigid line, which is directly connecting the propeller to a machinery space, means that you have more flexibility in smoothing out, finding the optimal hull form for your vessel. Additionally, usually for maneuvering capability and steering capability, the best adaptation of pod propulsion is to push them as far in the outer back corner as possible. And that means for a shaft line solution, you would actually have shaft lines protruding more or less outward, which is not necessarily a good performance design. Right, so if we look at the current outline of our product family, we've divided it slightly into different categories based on technology and based on design principles for it. So if I start from the right, this is basically the big ice-breaking unit. So today, a majority of icebreakers around the world are basically designed with our VI type Azipod. It's designed up to roughly PC2 ice class, which is at the moment PC2 is actually the highest ice class that any vessel has been built to. So yes, there is a definition of PC1, but for instance, I was just reading about this Commandant Le Charcot cruise vessel, which is a PC2 vessel, and operating in the Arctic that it actually crossed the North Pole. It has our Azipod propulsion and it's a PC2 vessel, so it crossed the whole North Pole on its own this last summer season. So definitely a robust and capable unit in that sense. Next to that, we have a slightly smaller, so we see from the power range that this is from 6 to roughly 17 megawatts, a slightly smaller unit for high ice classes also. So we're going up to PC3, which is polar class 3, so definitely a ice class which correlates to operation up in the high north or down in the south. So definitely high class. This is based on a permanent magnet technology, and the cooling of the motor is strictly to the surrounding seawater around it. The EXO, which is primarily from around 14, 15 megawatts up to 22. We have done some downscaled versions of the 12 megawatt, but it starts to be a bit too big a installation for this kind of sizes. So that's also as the big ice going unit based on synchronous motor technology and is solely air-cooled from the cooling air system. This is the prime mover of the cruise industry today. Here, the M size, which is our newest frame size. This is starts to be 5 to 10 years old now, is the newest member. And one of the main factors here is that we tended to have a gap in this power range. The reason for that gap was that the permanent magnet technology was not really mature enough to fit in there, and at the same time the synchronous technology was basically too bulky and complex to fit into these solutions. So hence it's from around 10 years ago when the permanent magnet technology in motors was developed far enough to actually accommodate for powers up to around 14.5 megawatts. We introduced this M frame size Azipod to the family. So the M size is basically coming from the experience that we have from the D frame size and the benefits from the EXO. So combining those two into a new frame size. So, and this is the mentality that we've gone through the years in developing our product portfolio. So always looking back into what we have, what has been the right solutions, what has been the working solutions, and then incorporating them and trying to reinvent, not trying to reinvent, but utilizing the knowledge and scaling it or making it suitable for a different frame size. So that said, last but not least, we go from roughly 1 megawatt up to 7.5 megawatt in this frame size. We do have a nozzled or a set of nozzled versions also for this, basically for the offshore industry mainly. But so there's a couple of different changes. This is again mainly focused on permanent magnet technology. We have some with induction motors, but the main driver is generally the permanent magnet, and then also mainly cooled to the surrounding seawater, but we have a cooling air unit on top of that to boost the performance. Right. So what we have in them in a nutshell, it's actually quite simple technology in that sense. So we have a propulsion motor in the middle that has directly mounted on its shaft a fixed pitch propeller. We don't utilize controllable pitch propellers. The reason is that the motor in itself is controlled with the frequency drive, meaning that we will always be able to change the RPM and hence control the power and RPMs of the motor. So it's having CPP on this one would be a bit of having two systems on top of each other, which is a bit surplus. The bearing arrangement is so that in the backside, so yes, coming back, the system is generally always a pulling system. So we're going from the left to right. So in the back, we have a truss bearing, which is also equipped with a roller bearing to take the radial loads on it. Same time, we have in the front, we have a roller bearing to take the loads from that. And then for allowing for that steering capability, we have a slewing bearing and a slewing seal here. On the different bearings and seals, we have slightly different solutions in different products. So for the smaller ones, we tend to have a face seal and then a lip seal, two lip seals as a double for that to make it redundant. Whereas on the larger ones, we tend to have a system of 4 lip seals to govern the sealing. Similarly, we have different solutions for the slewing sealing also. Is it oil mist lubricated or grease lubricated and so forth. Then what you would see inside the vessel is primarily the slip ring unit, which allows to transfer the power and data coming back and forth from the unit. We have steering motors, primarily today electric steering, apart from the ice going vessels where we utilize hydraulic steering. The reason for utilizing hydraulic steering in the icebreakers is basically that there are occasions when the ice load pushes, basically becomes too much from a side and pushes the pod around, and hence a hydraulic steering will give way and then re-engage directly, whereas with electric steering there are challenges usually with the clutches in repetitive work as such. And as said, I'll come back to the cooling system in a minute or two. So yes, the cooling is basically built on a closed loop system. So this is the same system in every cooling system that we have. It's a closed loop. We're not taking in additional air during operation. We have a water battery, which is connected to the vessel's cold water pipelines, which is chilling down the air. Then we have a fan motor that is pushing the air in one direction, down through the motor and up in the other end. In the exhaust, the cooling air is actually coming from both ends, and then it's rising the warm air from the middle of the motor. Now, these are also today mainly controlled by a frequency controller. So principally, when the sensors inside the motor indicates that the temperature starts to rise, only then do we actually start to engage the fan motors. So it's a bit of on slower, lower powers we can operate without this fan in normal conditions. The reason for the PM motor is basically its supreme efficiency compared to an induction motor. We have some induction motors also in the smaller units, and primarily those have been there to accommodate for, in some occasions, price, in some case preferences or power steps where we are shooting it in. So why pod propulsion? Well, this is a quite a good picture to describe the benefit from a hydrodynamic point of view. So on a conventional shaft line, you of course have the shaft, you have brackets, you have the rudder, you have usually some sort of stern thrusters, etc. And this then accommodates for about 5 to 10% of resistance for the vessel. So resistance increase means, of course, that if you look at the effective power, it increases by 5 to 10% also. So from a get-go, when you go to pod propulsion, you actually, as a starting point, already have a request for 5 to 10% less power need. We will, yes, see some benefits there will be some losses if we go from mechanical to electric propulsion in the conversion, but that's more a question of where we then see benefits by going into a basically power plant solution where you then can choose how many engines and motor generators you operate depending on the power that you're requiring. So getting those engines to operate at optimal efficiency compared to a directly driving big combustion engine, which unfortunately they are great, but unfortunately are usually operated at not its optimal operational point. So you lose in that great efficiency because you can't actually operate it there. But this is kind of the starting point to see the effect and the efficiency gains and fuel consumption reductions with pod propulsion. So apart from that, one of the great inventions was actually to look at the maneuverability. And the example here comes from Carnival Corporation's cruise vessels that they built at the Helsinki shipyard in the mid-1990s. It was a 7-vessel series, so the first 5 ones were with conventional shaft lines and rudders, and for the 2 last ones they changed only the propulsion to pod propulsion. So there was no optimization in regards to the hull form, there was no optimization whatsoever to other performances except for changing from shaft line propulsion to pod propulsion. Now, one of the big figures that came out of that I talked earlier about the footprint inside the vessel. In this case, the saved footprint was actually 1,800 square meters, which had a huge impact on how they can accommodate the equipment and facilities inside the vessel. Another thing is that you can see this, one of the driving factor, you can see this turning circle, which in effect is reduced by roughly 40%. In this case, we're actually looking at 2 different helm angles also, so it might be reasonable to say that it's actually reduced to around 50% of it. What's not shown here is that also if you end up in a crash stop situation, by turning the pods around, you effectively stop the vessel in roughly half compared to a conventional shaft line by changing the propeller rotational direction. Another thing, which is just a second. Another thing which is beneficial in that stopping movement by changing turning the pods around is that when you go when you do a conventional crash stop, you basically need to get the propellers to start rotating in the opposite direction. That means that there is a occasion when you're not actually generating any thrust in either direction because it takes some time to change the direction. It also means that there's a time when you're not actually requiring power from your power plant. So now you also, all of a sudden, you also have the engines which are producing a certain amount of power. They all of a sudden produce a surplus which you need to handle somehow in the system. So there is a added risk of a blackout in that respect. What also means that if you don't have thrust on a propeller and a rudder, you actually don't have a steering capability. So on a conventional shaft line solution, when you do a crash stop, there is a time when the captain and the helmsman actually also turn into passengers. They don't have control of the vessel. What happens with the pod solution, because you're turning them around, you have a constant thrust on the propeller all the time, which means that from the power point of view, the power plant is producing the same amount of power all the time, and it's being consumed. Additionally, because you have that positive thrust all the time, you actually have full control of your steering surfaces or steering capabilities. So you keep track and you keep in control of the vessel. Now, these are great things per se, but probably would not have ended up being such a successful product in itself. But the fact remains that what actually turned was this reduction in resistance that we spoke about earlier. So on this vessel series, the fuel consumption dropped by 8% between the sister vessels. And now we have to remember that there was no optimization yet for the hull form, etc. So spending some time on that, I would assume that in this case, we would also have been probably reducing the resistance by 10-12% at the same time. However, coming back to the comments about the steering capabilities, we have a simulator here in Helsinki to train the deck personnel on vessels. And in those options in the simulator, we have two ferries. They are identical vessels, but the only difference is in the propulsion lineup. So one is a conventional shaft line, and the other one is a pod propulsion. I'll jump to the next slide where I have a bigger picture of this graph. So what we have is the orange is actually the shaft line solution. This graph is from a case where we started up with 15 knots vessel speed, and the turning is with plus minus 15 degrees. So significant helm angle, but this is more to show the point how it functions. And I can tell you that I see the same phenomenon happening also with smaller helms angles. So coming back to the shaft line, what happens is that when you turn, your required power shoots up basically to the maximum that you can get from the system. Here it hits the power and torque limit, and then it's going to be hitting the torque limit all the time. So trying to rotate the propeller, but there's a torque limitation that it would require more power. Hence, it's dropping in vessel speed down through the maneuver. So in the end, the shaft line solution ended up going on average something like 9 knots through the maneuver and consuming around 10 megawatts of power. The pod solution, on the other hand, it's not as aggressive in dropping in speed, and that's because the increase in power is less pronounced. So we end up in a situation where through the maneuver, we end up at something like 9 megawatts, and on top of that, actually keeping a speed of around 13 knots through the maneuver. So altogether, the outcome is that basically a podded vessel goes through the maneuver with higher speed and less increase in power. Now, why does this happen? One of the primary factors, if we compare the system here, what happens is that with the shaftline solution, you have a constant propulsion power in the shaftline direction. When you turn the vessel with the helm angle, yes, you introduce a side force, which is then turning your vessel. But at the same time, you increase your resistance component from it. And also there's the resistance component coming from the side force. So what happens when you're operating is that you're increasing your resistance. This is, well, you're blocking the flow effectively. On the other hand, when you turn with the pod solution, your primary thrust component is turned. So yes, we can deviate it to a side force and an axial force, but in effect, what we're doing is that we're redirecting the thrust so that we're generating that instigation for the vessel to start to turn. However, at the same time, we're actually turning the propeller with the pod. So instead of introducing a component at an angle blocking the flow, we're still inside the slipstream of the propeller in the same way as it's been in normal operation. So we're not seeing the same increase in required power in the same way as you would see with a rudder system. Now, I mentioned that this is for 15 degrees. So 15 degrees is definitely a impacting helm angle. It's not something that you do by mistake, or if you do, then it's truly a mistake. But it's a considered, planned helm angle. So nothing that you're going to do too often during your sailing. However, we see the same thing going down all the way to, well, the smallest angle I was looking at was 5 degrees, and we saw the same trend happening there. When we turn with the rudder, we increase in power and it stays at a higher required power compared to the pod solution, and on the shaft line, it has a bigger impact on the vessel speed. Now, probably should have gone to smaller angles also, but that's smartness in hindsight. But what that effectively means is that 5 degrees starts to be an angle that you see, for instance, in autopilot systems. Or 5 degrees might be an angle that you're constantly introducing and operating under to compensate for sea states, wind conditions. So you might end up with the vessel which is operating across the Atlantic or Pacific Ocean with a constant helm angle. And this is where we start to see this increased and constantly added resistance and fuel consumption for shaftline vessels. Now, I said earlier that on average, from the equipment in the stern of the vessel, we can reduce the resistance by 5 to 10%. So in principle, when we go and look at the self-propulsion test results, we anticipate to see something like 5 to 10% reduction in fuel consumption. However, what usually happens is that our customer tells us that they have higher fuel savings than this prediction would tell them. And one of the key issues here is that as long as you're looking at self-propulsion, open water graph, etc., that's when you're focusing on what your propeller is doing and what your power consumption is. As soon as you start to look at maneuvering and seakeeping, it doesn't really matter anymore. Then you're just looking at the vessel behavior. So no one is really paying attention to what's actually happening in model test size when these are configured. However, when I spoke with our clients and our captains, everyone was, yeah, of course, this is exactly what happens and this is what we see in savings. So a bit of a surprise, but definitely something to keep track on and keep in mind. Right. So I briefly mentioned in the beginning the differences in azimuthing propulsion compared to pod solutions. One thing here is also that if we start to look at reliability, we have a huge amount of bearings and gears inside this solution. One other thing which is not stated here, but because we have this void space inside the pod, this is mainly to do with the cooling, but also the fact that we have an electric motor and so forth. This is air-filled space, whereas on a mechanical thruster, this would be filled with oil. So that's a huge amount of oil, which needs to be replaced, and gear oils, etc. It's not the cheapest solution here. A few numbers on our reliability. As said, we started in early 1990. In the beginning, there wasn't too much an impact because there wasn't too many vessels sailing, but we can see the impact of the fleet increasing in size, and we're currently talking around 30 million operating hours and on higher, basically a reliability of 99.9%, something in that region. So how we analyze this is basically to say that we have our sailing fleet, we have estimated hours on how many hours each vessel operates, and if there is a occasion that for some reason the vessel loses time, be it pod malfunction in some way that it can't keep up the speed, or in worst case it needs to miss a harbor call or something like that, then we reduce the hours, and then based on that we calculate how many operating hours we have had compared to the total possible. So huge numbers in that respect, and we're gaining more and more experience as we speak. From maintenance point of view, this is shown for the smaller units. So there are a few differences compared to the larger ones. The larger ones with the synchronous motors, those actually have a requirement because of the magnetizer inside it, etc., to have a human access to the unit. So basically there is a service interval of around once every half a year for someone to have a look inside the pod unit on the larger ones. On the smaller ones, going today up to around 10-12 megawatts, the whole approach has been that they are not accessible by a human except for during dry docking. So that means that the whole design needs to be robust enough that you can basically forget the whole functionality. So in normal operation with the smaller units, basically what maintenance there is from crew side to have a look at the indicators if we have any water coming in through the shaft seal. It's basically if there is any kind of leak, the water would then be dropped into the bilge of that unit and from there shut up to the pod room where we have an indicator glass for the crew to see that there's a slippage. At the same time, the crew would then see that if the fluid actually water or oil from the bearing system. Additionally, what they need to basically do is change some filters and then for the drives have some spare circuit cards if needed. But otherwise, from a pod perspective, the maintenance interval is basically built around 5-year interval, where the main focus is that the 5-year comes from that usually vessels are required to dry dock every 5 years. If you have a different interval, then we can recalculate how often the maintenance should be carried out. Additionally, a big factor is actually your operational profile. So this is built up with a cruise ferry, so up around 7,000 operating hours a year, and then based on that. But in short, what's indicated in black is something that you would do every 5 years when the vessel is dry docked. What indicated then in green is done every second dry docking, and what is in blue is basically falling under condition-based maintenance, but you should anticipate to do it once during the vessel lifetime. From installation point of view, this is now mainly for the units up to around 10-12 megawatts. What we do today is that we actually just have a flange connection between the vessel and the pod propulsion. So the only requirement for the shipyard is that we have a certain size of flange that they need to include in the vessel. The cooling unit, air unit, and the drives, etc., are usually placed inside the block during the block building, but the steering unit, steering module, and the propulsion module are then bolted from below into the vessel when it's in either dry dock or slipway or wherever the vessel is built. And this can be done basically just before launching the vessel. So timeline-wise, the equipment, the steering module and the propulsion module could basically be delivered to the shipyard like 1 month before launching the vessel, something like that. So definitely a lot later compared to a shaft line solution where you have to align and integrate the shaft lines at the really early stage of your building process. So in a nutshell, some reminder of where basically the best indicators come for pod propulsion. One is operational safety, in other words, maneuverability, capability to stop, etc. Designing point of view, flexible layout. You get a lot more flexibility in how to arrange your systems within the vessel when they are not rigidly connected with shaft lines. And then on top of that, the efficiency and comfort. I didn't speak too much about comfort yet. One reason is that with the pulling propeller, we have actually less disturbances in the wake field, meaning that the pressure pulses induced by the propeller is generally a lot smaller than in a configuration like this. So all in all, if I'm addressing a few words also on our current state with underwater radiated noise. We've been at it for about 15 years. So the main factor is basically that I'll show the next one. Okay, so principally underwater radiated noise is coming from 3 different sources. We have hydrodynamic, being from the water, usually up to around 100 Hertz. This is primarily where you see the propeller and its multipliers. We do see cavitation, for instance, deep vortex cavitation starts to push over to 600-700 Hertz, so could be somewhere around here. We have up to around 1000 Hertz, can be some sort of mechanical sounds coming from the vessel, so typical noise sources. But then for the electric side, we do see that the electric noise comes at high frequencies. It's depending on the drive. So the cleaner the electric signal that we can send to the pod unit, the less noise signature we have. So in other words, the pod hull form in itself is actually acting like an amplifier and a speaker for that noise signature. But having a good verified model that has been verified with multiple sea trials and noise measurements, we can see that from a default layout, which would be this green solution, we can go into a sideline mode. This is where we're basically cleaning up the stepwise control of the drive. We're not really achieving it, but if we throw in a sine filter also in it, it effectively drops the noise signature from the propulsion. So in this case, it's relating to DNV's silent class research vessel, which is the toughest class that they have. And in this respect, actually, looking at this, the high frequencies starts to be quite well concerned. The challenge would then start to lie on a conventional propeller, which is basically the same, independent of what kind of propulsion you have. In most cases, it's still a conventional propeller that you have at the end of the shaft. Right. We've been doing a bit on shock analysis as well. I'm not going to go into details in that respect in this, just to save a few minutes on time. I seem to be running a bit behind, but to say some words, basically performance, reliability, vessel signature is a big thing which is coming into play, and we see the life cycle cost and sustainability is of a significant impact, independent of what kind of vessel types you're concerning. So performance and reliability is significant for everyone. Performance might be on commercial side more in regards of emissions. On the Coast Guard and Navy side, it might be less fuel consumption driving to larger performance criteria. Signature is definitely in both cases, etc. So we see a lot of synergies going from vessel type to vessel type that you have a benefit in the system. Right. So in short, we're currently, this is from May last year, so slightly delayed, slightly old figures, but we would see some increase. So around 24-25 million operating hours. We've been at it for over 30 years. Currently, we see more than 35 different vessel types operating with both propulsion. Number of pods being in the pipeline or have been delivered is, I think it's closing up to 900 as we speak. At the same time, we're operating at powers from roughly 1 megawatt up to 22 megawatts. And noticeable might be also to point out that in this window, we have actually delivered everything. So there's no gaps in that sense that we wouldn't have a solution for you. Yeah, my current responsibilities are mainly in the Coast Guard and Navy segment, so hence the reference lists are also addressing a bit on that. But these are kind of the latest ones that we are allowed to speak about in the Navy and Coast Guard segment. There are some new coming out, but we haven't yet had the permission to talk about them. So that was a presentation on what pod propulsion is, and I would be more than happy to answer any questions that you have in that respect. If it's okay, I'll stop sharing the screen so that I also have a bit of a better understanding who's following up. Thank you.
Yeah, thank you. Thank you for the nice presentation. That's been very informative and enlightening. Mr. Andrei, thanks for the nice presentation. And let us see any questions coming up. I don't find a question here in the box. Let me see. Okay, so what I think maybe I can start. So let others come up with the questions what they have.
Yeah.
So yeah, it's a good thing. You're saying that there is about average 20% fuel saving on the use of port propellers compared to conventional propellers, and also explained the importance in while taking a turn and how the port is getting oriented compared to that of a rudder in the case of a conventional propulsion system. That's a good information with regard to the hydrodynamics aspect of a port propellers. And while coming to the also you mentioned about the the shape optimization, the freedom to adjust the shape of the hull as you have the freedom to put the engine away from wherever you want in the ship. So because it's electric propulsion. Okay, considering these aspects, and another major aspect, what I think is about the, as you said, is a reduction in the noise level compared to conventional propellers, which is of great interest to naval vessels, particularly which operates, as you mentioned towards the end about the signatures and creating more signatures noise. So I know that's the DNV class, silent class, which was earlier depending on conventional propulsion system. Later they modified or they included the Azipod propellers. So what's saving? What's the difference with regard to the noise reduction when you consider the use of port propellers and conventional propulsion system?
Well, in regards of noise, I think that currently we're basically matching up to the requirements from the DNV's criteria. That said, we have to remember that every project is specific. So we're basically doing a product-specific propeller design and so forth. So in the end, it comes down to choosing what you're optimizing for.
Okay.
Is it efficiency? Is it noise reduction? What's the driving factor? And in that respect, I would say that we're not necessarily at a level that we would be more silent than a conventional shaft line. I mean, if you look at what's happening in the Navy sector with silent drives and so forth. They might have a benefit, but we're reaching levels that should be quite acceptable in regards of research vessels, in regards of commercial vessels, etc. Not to mention certain Navy vessels also. But again, the highlight here is that we need to choose what we are optimizing for. So that's a process that would be done with the customer to design what are the propeller design criteria, basically.
Yeah, it's in continuation to that. If you want to enhance the silent class, or if you want to reduce the noise,
yes,
as you said, there may be a compromise or reduction on the efficiency of the system. So in any relation or how much it's going to happen, I'm just asking maybe qualitatively. Quantitatively, you may not be in a position to tell it now, but it's qualitatively, if you increase the silent nature of the vessel, so what would be the, compromise going to be on the propulsive efficiency of the system compared to the conventional one?
Well, if we're talking about a research vessel, for instance, the DNV silent notation goes up to, is specified for 11-12 knots. So say a research vessel where the operational speed would be 15 knots. Optimizing it for silent operation at 11-12 knots, I wouldn't necessarily see that big an impact on efficiency. It would be marginal. Okay. However, if we're looking at the vessel which is required to operate at 22 knots, so you need efficiency to gain that speed, but at the same time has a restriction, for instance, in noise signature. Again, the DNV classes and ICES is referring to this 11-12 knots, which basically means that the propeller needs to be cavitation free at that speed. But we do see requirements where the cavitation freeness is increasing to 15 knots and so forth. Then you start to see a huge impact also on the efficiency of the propeller. You need to increase your blade area, etc. So then we're up to, I don't know, but we could be easily 5-10% losing in efficiency. So it is a balance on what can be done.
Yeah, and maybe one more question about that is about the pod propellers. I've seen that one of the slide, it's gearless.
Yes.
So that means, do you say that the motor RPM and the propeller RPM are same? It's a direct drive?
Yes, they are directly connected. So the propeller basically sits on the motor shaft. Okay, so how the power requirement, how is depending on the power variation, how the RPM is going to differ, or what is the criteria in which the RPM of the propeller, you want to change the propeller RPM or increase the propeller RPM to get higher thrust. So that means how they are related, the power versus the RPM. Well, the power related to RPM goes directly with the equation that the power is the same as 2 pi times the RPM times the torque. So in effect, the torque is the driving factor or limiting factor, either case with the electric motor. So on an electric motor, you can achieve more or less a constant torque. It depends a bit on the technology. On a permanent magnet, you get the maximum torque right from the beginning. On a synchronous motor, you need a bit of RPMs, and then you have this maximum torque. So once you have the maximum torque, to increase in power, you increase RPMs. That means that if I compare, for instance, the big ice-going units and the big open water units, the difference is that they are basically based on the same electric motor. However, the power in the ice-going units is extracted during bollard pull to allow for ice breaking, which means that it's usually on a slightly lower RPM, because then in open water the RPMs are running away upwards, whereas the open water, say a cruise liner or whatever, it's designed to have its maximum or operational speed at that kind of maximum torque limit there, and then it's less RPMs upwards but more RPMs downwards where it's operating. So it becomes this balance on where exactly the propeller is behaving and acting, because we do need to remember that it's a fixed pitch propeller. So from a propeller design point of view, I could argue that maybe a bit lenience on a controllable pitch would be, but then on a day-to-day basis, it's still going to be RPM controlled. So it's not really giving the benefit that you would if you would have an incorporated CPP in it. So CPP gives something somewhere, but not really in this system.
Okay, I think maybe we will listen to, yeah, I got a question in the Q&A. Should I, connecting is asking, are permanent magnet motors useful in reducing the overall noise level? I think you'll be able to see that. You're able to.
I'll just open the chat and
Are you in a position to see the Q&A?
Can you repeat the question? Just.
Yeah, it's a question. It's from Mr. Amar Jyoti Das. It's asking, are permanent magnet motors useful in reducing the overall noise level?
Yes, they are extremely good at reducing the noise level. So that's actually why we have the best control on the noise level at around from 1 to around 10 megawatts, because in those we utilize permanent magnet motor, and on top of that, that's where we have our low voltage drives, which have a really good control capability of that magnetic flux that is controlling the noise level.
Oh, very good. Okay, so one more question from, I think the name is not clear here. What is the maximum diameter of propeller with Azipod? Maximum propeller diameter in Azipod.
Again, I would return to this fact that with an electric motor, you have this maximum constant torque. And when you include that to the RPM to get the power, then you have then you have the RPM where your propeller needs to operate. Now, this will then depend on the vessel speed, how big is the most suitable propeller. So it will be a design criteria on that specific project on defining how big a propeller would be suitable for that. That said, our biggest delivered propeller, if I remember correctly, was 7.5 meters. On the large cruise liners that you see operating today with powers of around 20 megawatts per unit, those tend to be around 6-meter propeller diameters. And then we go downwards. So it's, if you have more torque, you can have a bigger propeller. That's
right. So that means the 7.2 meters, what you said, is for the 22 megawatt engine, right?
No. That's actually for this all double acting tankers. So they had those criteria to perform in ice operation, but it's still a tanker, so they wanted to have a big, slow moving propeller.
Okay.
So it's I think the power is somewhere around 14 megawatts. So what we're doing there is that we're utilizing a huge torque with low RPM to enable a big propeller and have that punch to rotate it still.
Okay, so there's another question from Mr. Krishna Kumar. Can I just press the answer live, Dr. Paridwaja? That should work.
Yeah, sir, I can.
yes, sir.
Yeah.
Please. Actually, he had put the question in the chat box.
It's
yes,
there in the chat box. Okay, I mean, if he wants to.
Yeah, so I can just read the question, sir. Can you
Yeah.
add some remarks on a DP2 with Azipod, and if stern thrusters can be done away, and what will be its implication on the sizing of? Probably he meant the vessel. He's also the panel. Perhaps, if you can permit, he can just ask the question live, please.
Yeah.
Mr. Krishna Kumar, yeah, please.
Yeah.
So
Can you hear me? Am I audible?
yes,
Yeah, you're audible.
Please go ahead.
Yeah. So thank you for the good presentation. Now, my question was, if Azipod is used in a DP configuration, DP2 configuration, can the stern thrusters be, be dispensed with? And in that case, what would be the design considerations for a DP vessel with Azipod? Do you have more units, etc.? Where do you get such design choices? How do you go about it here?
yeah. Well, to start off, regarding the stern thrusters, absolutely. There's no reason to have them if you have Azipod propulsion. So Azipod, you will be allowed to have basically, if we're talking about the DP2 vessel, it's slow speed, probably designed to actually allow for full power in every direction, 360 degrees around. So that said, you definitely won't need additional tunnel thrusters in the stern. At the same time, a DP2 requirement will come into play then on your redundancy of how many different thrusters you have. So at the moment, I would say that the DP2 vessels that we see is mostly so that they have two Azipod propulsors in the stern. But because of the requirement of DP3, that DP2, you might end up with the retractable thruster in the bow. So it's a balance on what the requirement, how many redundancy factors you need to achieve the DP2. But basically, if you look at the required thrust that you can achieve with the pod, usually one pod will outperform any tunnel thrusters or configuration of tunnel thrusters that you would otherwise have in the stern.
Yeah, thank you.
Thank you.
Are there many installations with DP2 Azipod?
There are. Do I have a number? Not directly. We have a fair share of offshore vessels in different operation where DP2 has been a figure. And at the moment, we're actually, I think this last year, we introduced our own DP2 system. So that means that there's more and more DP2 vessels coming out also in that respect. But do I have a clear number for you? No, unfortunately not. But say, I would guess 10, 20, something like that.
Okay. Thank you.
Okay. Any questions from the panelist? I have one or two more doubts, but I'll ask after, any questions from the panelists. Dr. Paridwaja, you have like to ask?
There are no questions. I mean, it's still open, but there are no further questions from the audience as of now, sir.
Okay. No, I just would like to clarify.
If you permit, sir, I just have a small question.
Yeah.
What about the use of this Azipods in, say, inland transport and river transport? Are they examples of it? Particularly because we'll be operating with current. That's the reason why I was asking this question. And the
sorry,
sizes are smaller.
The sizes are smaller.
The sizes are smaller.
Up.
Sorry, I was just trying to ask whether there are instances of Azipod in inland transport, because the sizes will pretty much be into the smaller end of your Azipods?
Yes. So in principle, we have some, but they are larger electric vessels, definitely. So the challenge for us is basically that as a whole, the smaller units are not really economically feasible. So it means that the whole production line would be more of a mass-produced unit, whereas we may be a bit more on the bespoken design in that sense that we're doing specific designs for every vessel and so forth. So hence, for us, we have always seen that 1 megawatt is more or less the kind of balancing. We have some deliveries where we go to less than 1 megawatt, but then it's a question that there is a driving need for the owner that they want our solution. Additionally, if you go to that power range, there is also a lot more competition.
Good. Thank you.
Okay, so what I've observed from your presentation, some of the ports are having a fin at the bottom of the port, some do not have.
Yes.
So what's the purpose of providing that fin in the ports?
I got this same question the other day. So the main reason for the fin is actually to stabilize the azimuthing torque. So the steering torque around the azimuthing axis. When we have a fin, it's balancing out so that we have less torque requirement on the steering equipment. That said, that is the main reason why it's there. The benefit is that it actually increased also the efficiency. So it has
sorry.
Yeah.
Okay. Yeah. No, I'm just asking why it's not required for other ports. I mean, only for.
Then, yeah. So why we don't see it on the ice-breaking units is that at the same time, the risk in ice fields where you have ice rubble and so forth, the added risk of having a big ice piece knock it off is increasing the security of the pod in that sense. So that's why we don't have them on the ice-breaking units.
Okay, that's nice. And one more, maybe last question for me is, do you expect the strut which connects the port to the HUD, can it be need to be fully submerged, or it can be surface piercing?
So
yeah.
Yes, so the bolt connection can be fully submerged, and even say as an example for the nozzle units that I showed, on those we actually have a option also to have a underwater dismountable unit. So we had back in the day we had a drilling rig equipped with 8 pods, and they did so that they had a maintenance program where they had 2 spare units, and then without dry docking the vessel, just dismounted and remounted new units 2 at a time, took them to the shop to service, and then 2 and 2 and 2. So yes, definitely the sealing, the slewing sealing, etc., fine to be underwater. I think we have a limit of something like 10 meters on the conventional design. On the, as said, nozzled with underwater mountable, that's something like 40 meters.
Okay, thank you. If I think no more questions here. I think
there's just a question which got added.
Yeah, please go ahead.
Yeah.
I think there's just a question which got briefly added. I'm just wondering, can you add that question again? I just saw it very briefly.
The Azipod efficiency. Yeah.
Mr. Vinod Kurup has joined, and he only put the question, please.
Yes. So if we look at the Azipod efficiency, it's similar to a conventional propeller efficiency. So I probably should start drawing some open water curves here soon. But in principle, when you have that hump where you have your propeller design, just a second, let's see. Can I get the whiteboard? Yes. Okay, let's see if this works. So if we look at a let me just draw up something. Let's see if this works. No, not text.
You can use the pencil like for
Yes.
freehand sketch. Yeah,
So,
on the left side.
You may excuse my drawing skills, but principally, if you have a propeller curve like this, you would have the thrust and torque coming, something like that. This is not the most beautiful design per se, but you would do your propeller design for let's say that point. Now, if that would be for say 20 knots operational or something like that, it still ends up in a situation where your RPM with a fixed pitch propeller will basically go hand in hand with your speed, so that their relationship is more or less constant, starting from maybe something like 8 knots up to your design speed of 20, something like that. So if you look at this design point, the window where you would be operating, it's quite small on either side of this design point in normal operation from around 8-10 knots up to your design speed of 20-22 knots, something like that. And for the pod propulsion, we basically do so that instead of having values separately for a propeller, we're actually generating the open water curve for the whole unit. So it looks like a conventional propeller open water curve, a bit like what I drew here, but it's more smooth and so forth. But yes, so an Azipod efficiency remains more or less the same across its operational points. What happens with draft is, of course, that your resistance reduces if it's less draft, otherwise more. So it would be basically moving back and forth on this curve, depending on if we have an increase in thrust needed or reduction in thrust needed. I hope this somewhat explained your or answered your question.
Okay, thank you so much. Thank you.
Yeah, thanks a lot. Maybe I would just the last question from one more question. I just thought of it. The electricity required for the port propulsion unit is being developed using diesel electric drive-set engines, right? Am I right?
Well, diesel electric, LNG electric, in some cases fully electric. We're also looking at providing also fuel cell options, etc. So in short, we need electricity. We're not that keen on how it's produced.
No, my question is, if you look to the emission part of it,
yes,
using generators, diesel generators, generating electricity and running the port, and at the same time using the conventional engines to run the conventional propulsion system.
Yeah.
How do you find the emission characteristics of these two systems?
Well, as I briefly mentioned during the presentation, one of the key issues with if you look at now, it's depending slightly on which level we look at, but basically any way we go to electric propulsion, you need to have a power plant approach to it. In other words, you have gensets, be it, as you say, diesel, be it whatever, which is producing the electricity. If we compare that to a conventional engine approach, then traditionally that engine will be directly connected to the propeller. You could have some gearing, you could have some approaches and so forth, but on average you will have a engine which is designed for the maximum output of that shaft line. So what happens here, we had a close look at this when we were studying LNG carriers. What happens is that combustion engine is designed for 19.5 knots. The vessel seldom operates actually at 19.5 knots, so it's operating at 15, 16 knots usually, which correlates to boil off from the LNG. But point being that when it's operating offside its peak design point, it's actually operating at less efficiency. Now, what happens when you go to electric propulsion? You approach it by saying that, okay, now I have a power plant solution, which might be a question of, instead of having one engine, I have 2 or 3 or even 4 gensets. So if I'm operating at a load which is 1/4 of the required, I actually have one genset operating, and then the engine is operating at its best performance level. If I increase the power, I start another one. So what comes out of this is that in conventional, if I have one shaft line, one engine, I will slowly rise up to that best efficiency at its design point. But the majority of the time, I'm operating at off design points. Whereas if you go to the approach of having a power plant solution, you will get kind of these bumps, but at a higher level, because depending on how many engines you put in or gensets you put in, they will always reach the best efficiency. So that gives you this added value there. What you can also do when you go to electric and you combine it with batteries, you could end up to operate at, say, if we say hypothetically that you have you reach your best efficiency point with your first genset at 9 knots and your second at 12 knots.
Yeah.
Now, for some reason, you want to operate at 10 knots or 10.5. So that means that it's going to be that dip between them. What you would do then is to actually start 2 engines, operate them at the ideal efficiency. You're overproducing electricity. But that overproduction, you feed into a battery system so that after a while, when the batteries are full, you shut off one of the engines, jump into only one engine, but now you're underproducing. So now you're taking that added energy which you earlier produced and stored in the battery to compensate, to keep going at 10 knots. So this is how you can play around with and here you actually see the benefit of electric systems, that you have this immense flexibility on how you do and how you operate.
So if you permit me, I just ask a quick question, sir, because of just what you just told. So some of this, because we were talking mostly about the hydrodynamic side, that's why we didn't talk much about the engine and the electricity side. But are you primarily using DC or AC drives?
Depending on the power and the technology. So principally at the moment we go with DC up to around 6 megawatts, and then we start looking at AC. But however, on the motor side, we still do AC motors.
Okay. Because the system you just now described, like there's a lot of power switching, AC switches and DC switches to design the power circuit. That's why this question came. If you can add a bit more on that, it would be nice, please.
And this is more or less where I just said that I'm a hydrodynamicist, so that goes over my head. I do understand something. Usually if the bluish smoke comes out, then it doesn't work anymore.
Actually, yeah.
Thank you. And any other question from
I have a question, sir. I'm Manu here.
Please go ahead. Yeah, please go ahead.
Yeah. Okay. Now you are a hydrodynamist as well as you are also doing a lot of marketing. So let me ask you, who are your competitors?
Who are my competitors? At the moment, this is in a sense a good question. It's an interesting question. As said, we've been at this for around 30 years. When pod propulsion was first introduced in 1990s, there became a hype. Everyone wanted to do it. Every electric company wanted to do it. So Alstom had the Mermaids. Siemens had a collaboration with Schottel. GE was playing around there somewhere also. But over the years, they all more or less disappeared. However, that said, now we have Kongsberg, which, if you dig into it, is actually going backwards to being Rolls-Royce and old Alstom players in it. You have Siemens again, trying again to launch something. You had GE trying to do something with the ice market. They built a factory in Russia just before the Russian invasion war started, so that didn't succeed really well. But what I'm saying here is that in principle, we're seeing the situation that the same companies have tried before and are trying now again to get into the market. We've been here all the time. We've been growing and developing the product all the time. So, of course, by all means, we do have competition, and especially in China, we start to have local competitors. But there needs to be also a question from the customer side that what do I get with someone who has tried to get into the market, not really succeeding that well, or someone who has been constantly in that space and managing quite well, I must say.
Okay, thank you.
You're muted.
Yeah, Dr. Manu, done?
I have, one small point. Actually, what I wanted to hear from you is, what is your edge, which is keeping you in the market? And when, the naval architects recommend Azipod, what and why we should recommend yours? What is that additional takeaway for your system?
Well, to address first, Azipod is a mechanical thruster. So then you would be in a situation again that you will have your prime mover inside your vessel. You will have a shaft line connection down to the propeller. Azipod has a good efficiency. That is hydrodynamically well designed, but it's still a mechanical thruster. It will be full of oil that can spill out. It will be full of oil that needs to be replaced also. And additionally, you have this combination of shaft lines and gearing that will introduce losses.
Excuse me. My question is not compared to the normal drivetrain. I'm, just trying with your competitors, who could not perform and who have not come to the level of expectation. Where is the difference? What makes your Azipod unique?
Yes. So then if we look at the Azipod in itself, where we have the the electric motor in it. Why I addressed the article is that you mentioned it yourself, so hence, I would say that a lot comes actually from how we have been run as a company. We have had constant support from the management. It's seen that it's a separate own entity which needs to be handled and respected in the space to make it work. So for instance, I know that some of our competitors were a combination of electric company and mechanical company, where they ended up more or less in a feud on who's actually responsible for it. In some cases, the focus has been so strongly on electric shaft lines that this pod has been kind of a separate small unit and never really seemed to have gotten the support from their company leadership in that respect. So again, I don't know what all is happening in that
then
space.
I'll specifically ask you, what I'm asking is, see, the hull and the propeller, generally, when the hull design is over, then you go for a propeller design. Here
Yes.
you have a standard product. So how you are facilitating a naval architect to function and to get the best efficiency from your system? I'll complete, sir. I'll complete, sir. So I'm just looking at how free the naval architects are to design their hull form with your system. This is one part. Second part is an extension of the question Dr. Bharadwaj Srinivasan has asked. That is the range of operation. If you have to consider Azipod, what is the best range? Like from what power to what power we should look at Azipod when we look at its utility for vessel design? This, the combination. Yeah.
Okay, so to begin with, we don't have a standard product. We have standard frame sizes for power windows that we utilize. The propeller will be a bespoke design for every singular project. So that means similar to normal operation that you specify your hull form and so forth. Now, where the difference comes is that we encourage you to consider pod design, pod propulsion from the beginning when you start looking at your hull form, because that will be dominating in the sense that where you place your equipment, how you place it, and how you achieve the best hydrodynamic performance. Say you have that flexibility to optimize your hull form. So in principle, optimize the hull form for as low bare hull resistance as possible. And then you place the pods underneath it. You don't need to take into account the shaft lines, etc. So you will have less. We have a power range of from 1 to 22 megawatts, which means that if you ask me what vessel would be suitable, it's anything that has a shaft line, power per propeller from 1 to 22 megawatts. You can have multiple units, you can have etc. Okay. So far, I haven't really seen a vessel where, if I'm honest, would have a negative impact of having pod propulsion. So for instance, if we're looking at, I don't know, merchant vessels, we're not strong in them. But at the moment, if I'm looking at merchant vessels, for instance, by going to a pod propulsion, one of the biggest factors is not necessarily on the propulsion itself, but actually going to this power plant solution, because the four-stroke engines and the generators are smaller than two-stroke engines. So you're actually increasing your cargo capacity in the vessel without expanding to bigger vessels. So you can stack where you have your machinery spaces, for instance, under your tower, and hence increase your cargo capacity, and at the same time benefiting from a better efficiency. As an example.
Sorry, the previous discussion with Professor Krishnankutty, you were nicely bringing out about the efficiencies when we generally operate the research vessels or say around 10, 12 knots, as compared to some sort of compromises you have to make when you go to 20 knot sort of vessels, particularly from the power plant side of you, even though you may get somewhat on a different parameter, you may get a better performance. From that point of view, is there any particular fluid number ranges? Because research vessels also typically are maybe, say, 70 to, say, 80, 100 meters or so. They are not really the 150 meter sort of thing. So in that context, is there any specific fluid number ranges where your azipods are? Probably I should look at azipods at some fluid number ranges in that sense. Because you already mentioned a certain speed, and the typical vessel sizes are those speeds and that sort of thing.
Yeah. No, not really. I mean, if I look at what we've delivered, so the smallest ones are small ferries. At the same time, we're delivered to the world's largest cruise liners. And the cruise liners operate normally between 20 to 24 knots. That in that range, we have a lot of different vessels. We have a lot of different vessels around 10, 15 knots. The highest speeds we have with the Japanese ferry, where we have this CRP concept, so that there's a conventional shaft line in front and a pod behind it. And those are operating at up to 32 knots. So yes, to try to give you an answer, conventional propeller range, not water jet or something like that. That's roughly where I would say. But at the same time, we do need to remember that if you have a light craft going at high speeds, we do have the pod with the motor in the stern of the vessel. So that might be a consideration if you go to really high speed vessels. Additionally, at the moment, our prime kind of design space has been around 20-24 knots. So that means that in our internal calculations, what we've designed them in mind has been in that range. It doesn't mean that we can't modify it to go faster. So again, we do a bespoke design for the propeller that will be defined for every project. At the same time, we have, for instance, this strut height, etc., will be modified for every project, etc. We don't, in that respect, have a standard design. We have standard templates for different powers that we then modified to suit your project. I hope this gave a bit of an answer. It didn't exactly answer your question.
No, it is basically just adding to what Dr. Manukarla was asking, how Naval Actech looks at the design space when you consider product propulsion, and your comments were certainly enlightening in that extent.
Yes, and this is one I would urge you to consider, to be in contact at an early stage, because one of the worst experiences I've had for the customer is, and this happens way too often, that you have a design which is already based on a shaft line solution, and then you want to change it to a pod solution. You will never get the full benefits of electric propulsion and pod propulsion in those cases. So the earlier pods are included into the design. You can have it as an optional, but at least give the freedom to optimize the hull form to match what you actually want to do.
Okay, I just one last question
Yes.
from my side. For an acoustically silent ship, so you propose for the speeds that it is supposed to operate, acoustically silent research ship, do you recommend Azipod, or do you think any other similar system could be better?
Well, I would obviously recommend Azipod,
Okay.
but to turn it around, I would say that at the moment we seem to be reaching the same noise levels as you would be with other solutions. So we're not necessarily improving the silent, but we're reaching the requirements. However, on top of that, you're getting better maneuverability, you're getting better fuel economy, you're getting better security in that respect. So it's more a question then that, okay, say you need to transport 4 people in a car. Does it matter what kind of car you're transporting the 4 people if they all fulfill what you require? Not necessarily. But if you can throw in that it's your family, you might want to have a safer car. You might want to have a better fuel economy on the car. You're still reaching the same end in that respect. But it's question what else do you want?
Okay. Do you have any ballpoint figure, any sort of figure about the noise level that it produces generally an Azipod?
Well, one was what I showed in the presentation. That was done as an exercise in respect of the DNV silent R notation, so research vessel. As said, it's a bespoke design on the propeller, and it needs to be optimized for every single vessel. So it's not that we have a standard solution that we throw in, but it's more a triggered and tweaked solution for that specific project. So in that sense, that kind of reference to DNV silent R notation gives a indication what can be achieved, but it will be a case-by-case design and optimization.
Andrei, if I may
Yeah.
jump here.
Yeah.
I think
please go.
we have there is similar question sometimes back regarding some customers from India for acoustic research as well as for oceanographic research vessel. So we have shared some documents that time. If Manu Kurula could contact me later, I can share the same documents with you.
Okay, fine. I think, yeah, it's not a question to
Thank you. I'll definitely consult you, sir.
Okay, thanks a lot. I think we are nearing the time. And so to sum up, it has been a good presentation, Mr. Andrei. And we have seen we got better exposed to port propellers now after your talk. And we have seen the flexibilities what are available with the use of port propellers, mainly on the hull form design, putting the engine room location, and other aspects we have seen. And also you said how to manage or optimize the emission characteristics by manipulating the use of the different generators and battery and all that. That's also a good information. And my feeling is also that when you use port propellers compared to conventional propellers, you see the flow-induced noises, I expect it to be more in conventional propulsion system because of the appendages. It's like radar, housings, and with the twin screw, the shaft brackets. These are going to introduce more flow separations and flow-induced noise, whereas it is expected to be less in the case of a forward propulsion system. So that's what I feel is a qualitative assessment. But as you said, again, depends on the vessel and how the port propellers are getting married with the design, what you do. And totally agree with you that instead of reaching the option of forward propellers at a later stage, it's better to start thinking of at the beginning of the design of the vessel, so that you get the best benefit from this forward propeller. So this has been done, and also you have covered the advantages, like you get 5 to 10% power saving compared to conventional propellers when you go for port propellers, and also the turning capabilities you have said with the port propellers. Then also coming to the crash stopping, you save a lot of time, distance compared to 15 times the length for conventional propellers. I think it may be taking less than half of the distance in this case. So, and turning also, we have seen since the propeller, the port is rotated, and it gives a full thrust in that direction, giving more moment for turning. And as you projected, it's going to take less turning diameter for compared to conventional propulsion system. So there are many advantages for that. And also you covered about the maintenance schedule of that. It's a normal thing, which you have said 5 years, what all things, 10 years, what all things, and once in a lifetime, the inline shaft bearings and all that. So that, so this, what you have given is a good exposure for us to the participants here. And we thank you for that.
Oh, you're welcome, and thank you for this opportunity. It was really, really fun.
I just hand it over to Dr. Bharadwaja.
Thank you, sir. Now, there's a message from the president of INA, Dr. Manu Kurula, regarding next month occasion. So please, sir, prior to the vote of thanks, please, sir.
Thank you.
Dr. Manu Kurula, yeah, you want to tell something to the INA community, please.
Respected Professor Krishnankutty, today's presenter, Andrei, Korsström, the panelists, Dr. Bharadwaj, and the members of INA and guests. Good evening to you all, and greetings from INA for the year 2025. Let the year be fulfilling for all of us and forthcoming. Today we had a wonderful session. I should say that he has actually opened up the whole code for us. We have had a very good understanding, and he has also told us the applicability, and he has brought us the marketplace so that we could take decisions. Thank you very much, Andrei, and we appreciate the excellent presentation that you have made for us. INA is planned to have every month the series lecture program, and the professional secretary, Dr. Bharadwaj Srinivasan, has planned to have in-person sessions at different locations in the country. Already the last year we have completed Vizag, and in the month of February 8th, we are going to have one at Calcutta. So that also you will be able to actively join through VC for viewing the proceedings. We are hoping that this year will be professionally fulfilling for all of us, and INA is committed to bring in more professionalism and more exposure for its members. This year we are hoping that we'll have a membership drive. I request all the members to bring in more professionals into the society. I once again thank each and every one of you for making it possible today. Congratulations to the professional secretary for having a wonderful speaker. And once again, I thank Professor Krishnankutty for chairing the session. Thank you and all the best.
Thank you, sir. Actually, you have also done the vote of thanks, but still I'll formally do it, the vote of thanks. It's my privilege to do that. First thanks is to Professor Krishnankutty, who had chaired the session excellently and moderated the Q&A session and actually initiated the discussion in the Q&A session. And I know his wide knowledge, and it made the session as lively as the lecture was. My thanks to the speaker, Andrei Korsström, 3.5 hours of difference. It started somewhere at 1 o'clock his time for us.
No, it's fine.
Thanks for sparing your Saturday afternoon and enlightening us with the product propulsion. Apart from the technical and practical aspects, I should just tell that I just admire your patience when we went on, and when we thought the lecture is going to end, and then another question. Thanks for patiently answering all our questions apart from your lecture. Very enlightening lecture, and thanks for it. And that was thanks to Mr. Fahas, who is your colleague. We met in a conference, and it was just an exchange of cards, and later we just connected for this lecture. So I should thank Mr. Fahas to have actually enabled the connection with you. Thank you. You've searched for the right person. Yeah.
Thank you for having me.
Yeah, and Dr. Manu Kurla, who is the president of INA and the guiding force behind this regular happening, which is happening every month. We started now 2025 at a very high note. I hope all the other 12 lectures will also follow the standards which has been set today. My thanks to the 26 participants who have joined online, and also all the people who asked their questions, which made the question answer lively. Thank you for all the participants, even though it is 26. One of the participants, if you kindly note, would have been NCW Delhi, where a large number of students are sitting in a hall. So the actual people who had actually watched it live from Chennai, Delhi, and the student community, it is also live streamed in a student hall. So the number of people who actually live heard this lecture, maybe around, say, 90 or so. And so thanks. I mean, that's attendance, and I thank all the people who have joined. And thank you. And have a great evening, great Saturday evening, and have a great year in 2025. Thank you.
Okay. Thank you all. Thank you. Bye.
Bye-bye.
Bye.